Hi guys, so today we're going to take a look at question 7 from 2015 paper 2. Okay, so we have a flat machine part consisting of two circular ends attached to a plate, and the sides of the plate are tangential to each circle. The radius of the larger circle is 4r centimeters, and the radius of the smaller circle is r centimeters. The length of HK is 8r centimeters, and AB is 20 root 73 centimeters. Okay, so typically at this point we would write down the information that they've given us from the question, but everything here is given in the diagram. All of this information is captured by the diagram nicely. The right angles because of the tangent, the lengths. So we'll just move on to part A. So part A, we are looking for r, the radius of the smaller circle, and it's giving us a hint to draw BT parallel to KH, where T is on AH. So it wants us to draw a line parallel to HK from B to the line AH. So something like this. Okay, so, well, what do we know about this line? Okay, well, so it's parallel, so it's equally distant from HK the whole time, which means that if this is T, then HT is R. Okay, so let's just write that down. So the length of HT equals R. Okay, and we also know that since these are parallel, since BT and HK are parallel, this line here cuts through the parallel lines, so we call it a transversal. And when a line cuts through two parallel lines, it makes the corresponding angles, which are these angles and these angles, or also this and this, it makes these angles equal. So since we know that this angle is a right angle, this angle must also be a right angle. So the angle of ATB is 90 degrees. Okay, so what else do we know? Well, if this is a right angle and this is a right angle, then we have something like this. So, right angle, right angle. Well, we can immediately tell that these two are parallel. So, TH and BT are parallel, which means they also stay equally distant from each other, which means that this is 8r, same distance from each other. So now TB equals 8r. All right, so now, well, if you see, we actually have constructed a triangle from T to A to B, B to T. We have a triangle here where we either have the length or we have an expression for the length in R, and we're looking for R. And furthermore, we know it's a right angle triangle. So when we have a right angle triangle, chances are we're going to be using a squared plus b squared equals c squared. Okay, so c is the hypotenuse, the length opposite the right angle. So c equals 20 root 73. And then a and b are just the other two sides. So let's just say that a equals 3r and b equals 8r. Okay, so if we plug this in, we'll get 3r squared plus 8 r squared equals 20 root 73 squared. So we get 9r squared plus 64r squared equals 420 squared by 73. Okay, so if we add these together, we'll get 73r squared equals 400 by 73. All right, so now we just see that 73's nicely cancel, which kind of makes sense. It would be really weird for them to just randomly make it 20 root 73. So r squared equals 400 and r equals 20. All right, so not too bad. Very nice with the hint that they gave us. And then just to see what you can figure out. Can you figure out any angles? Can you figure out any lengths? And then it just makes it nice and easy. Oh, and just a note here. We said that A equals 3r, so that would be, so one of the lengths of the triangle AT equals 3r. The reason we know this is because AH is 4r, we can see that in the diagram, and we know that TH, or HT, equals r, and then AT is just the difference, so it's just 4r minus r equals 3r. Now on to part B, we want to find the area of the quadrilateral ABKH. Okay, so first of all, let's just figure out what it is we're trying to find. So ABKH, the quadrilateral, the four-sided shape. So that would be here, 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 and here. Okay, so the four-sided shape ABKH. So this is what we're trying to figure out. And we want to find the area of this quadrilateral. All right, well, we don't really know how to figure out the area of a quadrilateral. But in the previous question, we split this quadrilateral into two things that we do know how to calculate the area of. So we split it into a triangle, a right angle triangle, and a rectangle. Okay, so let's have T here. So we have the area of the thing we're looking for, the area of ABKH, let's call it the quadrilateral ABKH, is equal to the area of the triangle ATB plus the area of the rectangle THKB. THKB. Okay, well, let's start off with the triangle. So the area of this triangle ATB. Okay, well, we know the formula for the area of a triangle. It's just half the base times the height, or more specifically, the perpendicular height of the triangle. Okay, so there's two ways of approaching this, and one is easier than the other. All right, so let's say if we take AB as the base, okay, well, we know that it's 20 root 73, and then this would be the perpendicular height, which we can probably find out, but it's a little bit of a pain. So an easier way of doing this would be to take AT as the base, and then the perpendicular height is TB. And we actually already know both of these, so this will be the easier way of doing it. Okay, so our base is AT, so it'll be half AT times the height, which is TB. Okay, and we know that AT is 3R, which is 3 by 20, 60, by 8R, which is 8 by 20, 160. And so this is just 4,800 centimeters squared. Remember, we're working in centimeters, so centimeters squared is the area, is the unit of volume here. Okay, so we've got this thing. Now we got to calculate the area of the rectangle. Area of the rectangle, THKB. THKB. All right, well, we know the formula of a rectangle. It's just the length times the width. Okay, so our length is HK and our width is KB. So HK times KB. All right, and when we know both of these again, HK is 8R, so 8 by 20, 160, and KB is just R, so 20. So this equals 3,200 centimeters squared. And the area of the thing we're looking for, the area of the quadrilateral ABKH, is the sum of these two, 4,800 plus 3,200 equals 8,000 centimeters squared. All right, now on to part C, part 1. Find the angle HAP in degrees to 1 decimal place. All right, well, what is HAP? Well, it's this angle. It's this angle here. Okay. And now the trick of this question is to notice that this quadrilateral that we've just worked with is the same or identical to this quadrilateral. These two quadrilaterals are the same, so the shape is symmetric. And the reason we know this is, well, this angle equals this because it's a tangent, so this angle equals this. This length equals this because it's both the radius, and this length equals this. Okay? So then if they're the same, well then this angle equals this angle. So let's just draw that out. So what we're looking for, the angle HAP is equal to HAB plus PAB. Okay, that's we can just immediately see that. And because they're equal, HAB is equal to PAB. Okay. And so then we can rewrite our formula for HAP as HAP is equal to 2 times HAB. All right, so now what we're looking for is this angle here. Okay. So how might we go about this? Well, again, it might be useful to have our BT because now we get to work with the triangle and we're more comfortable when we've got an angle. We're more comfortable working with a triangle than with a quadrilateral. Okay. Well, what do we know about this triangle? Well, we know that this is 8r, this is 3r, and this is 20 root 73. All right, and it's a right angle, so we can just use our sine formula. So sine of an angle of, let's say, theta is equal to the opposite over the hypotenuse. Hypotenuse. Okay, so if we let HAB equal theta, then sine of theta will be the length opposite HAB, so it will be this length, the length opposite our angle, all over the hypotenuse. So this will be 8r, 160 over the hypotenuse, 20 root 73. And this is just 8 over root 73. Okay, so that's what theta is. Okay, so, well, that's what sine of theta is. Well, and this will allow us to get theta. So we just go sine inverse of both sides. So sine inverse of 8 over square root 73 equals theta equals 69.44 degrees. Okay, so we have theta, but we're not looking for theta. We're looking for 2 theta. So that means that 2 theta equals just 2 by 69.44 equals 138.88, or to one decimal place, 138.9 degrees. And that equals our angle HAP. Now on to the last part of the question. Find the area of the machine part correct to the nearest centimeter squared. All right, so, well, what the hell is this here shape? Well, I don't know how to calculate it, but we can split it up into things we do know how to calculate. So let's say the area of the whole thing of, let's say, a machine part. Well, what is it equal to? Well, let's try and split it up into 4 sections. Our quadrilateral, the other quadrilateral here, this circle sector here, and then this circle sector here. Okay, so the area of the whole thing is the area of our quadrilateral AHKB plus the area of the quadrilateral APQB plus the area of this circle sector, the large circle sector, plus the area of the small circle sector. Of the small circle sector. All right, so this allows us to come at it one part at a time. All right, so let's start off with the area of the quadrilateral AHKB. Well, we've already worked out the area of this. So this is just 8,000 centimeters. Let's just leave that. 8,000. Okay. Easy peasy start. Now, onto the area of the other quadrilateral, APQB. Well, we know that these two quadrilaterals are equal. So they have to have equal area. So this would also be 8,000. All right, so now these are the two easy ones. Now we've got to calculate the area of this circle sector. Area of the large circle sector. Okay, how do we calculate the area of a circle sector? Well, we have a nice formula for this. So the area of a sector is pi r squared by the angle over 360. So if you think about this, it makes plenty of sense. If the angle was the whole thing, all 360, then this would just be pi r squared by 1, which we know is the area of a circle. And if it was, let's say, half the circle, 180, then it would be pi r squared by a half, which we know is the area of a semicircle. So this formula makes sense. But now we've got to work out, what is this angle? Well, what is the angle that we're looking for? Well, we're looking for this angle here. Okay, well, we know that this angle here plus this angle here, the remaining angle, should be 360. Okay, so our angle plus the angle HAP is 360. And we actually know what HAP is. We just calculated it. So our angle is 360 minus HAP minus 138.9, what we calculated HAP to be. So this makes it 221.1 degrees. Okay, and now we can just calculate the area of our sector. So the area of the large circle sector, let's just call that LCS, is equal to pi times the radius, which is 4r, which is 4 by 20, squared, by the angle 221.1 over 360. Equals 12348.55. Okay, and now onto the area of the small circle sector. So the area of the small circle sector, let's call that SCS. So again, we have our formula pi r squared by the angle over 360. Okay, well, our angle in this case is this thing. Okay, so the angle is KBQ. Okay. And so let's say we extended AB. Okay. Well, we might notice that let's call this C. We might notice that KBQ is equal to KBC plus QBC. So similar to what we did for finding the angle HAP. So we're gonna zoom in on this shape here. Okay, we're gonna zoom in on this. So if we zoom in on that and then rotate it so we can look at it properly, we'd get something like this. Okay, where this is B, this is K, this is H, and this is A. Okay, and then we extended this to C here, and we're looking for KBC. We're looking for this angle here. Okay, well, we know that this is a right angle, this is a right angle. We know that these two are parallel. Well, then that makes CBA a line that cuts through two parallel lines, which means that the corresponding angles, so in this case the corresponding angles here and here, are equal. All right, so now we've seen that HAB, angle HAB equals KBC. Okay. And in the same way, QBC is equal to PAB. So in the same way, this angle is equal to this angle. Because remember, these two shapes are the same. Okay, so PAB equals QBC. Okay, and we know HAB and we know PAB because the sum of these two, so KBQ, so KBQ equals KBC, which is HAB, plus PAB. Okay, and we know that these two, the sum of those two angles is just this. HAP, which we know as 138.9. And now we have our angle. Now we can just plug into our formula, area of the small circle sector equals pi times the radius, 20, squared by the angle, 138.9 over 360. Equals 484.85. Okay, and now we have all the four areas that we need. So the area of the machine part is 8,000 plus 8,000 plus 12,348.55 plus 484.85 equals 28833.4, or rounded to the nearest centimeter, just 28833 centimeters squared. And that is the answer. So just break it up into manageable pieces and then go through the pieces step by step.